In this video, I'm going to do an example where we estimate the parameters in an AR1 process giving some time series of length n. So our data is the following. And the model, remember, is that where the u of t's are assumed to be independently distributed random normal draws. And you see that y1 is dependent on y0, and so we're going to do everything conditioned on knowing what the initial value is, that y of 0 is known. And we can write this process in a vector matrix form or in vector form as follows. Where so the y tilde is just the original vector of y, but shifted so that we can stick y0 as the first entry, and we only go up to yn minus 1. So this is the origin of the word. The name autoregressive is that y is regressed on itself. And then the noise variant, the noise vector, I mean. All right, so to get started, we're going to write down what the likelihood is, and we're going to start by writing down what the probability of u is based on this model. So probability. Now this is the u's are going to come from a multivariate normal, which covariance matrix C, which is given by sigma squared times the identity matrix. What I went to write was the precision matrix, which is equal to the inverse of C, which is going to be 1 over sigma squared times the identity matrix. So this is the covariance matrix, sometimes called the variance covariance. And this one is the precision matrix. They are just inverses of each other. All right, so from this I can write, this is the normalization constant. So this is the probability distribution for the u's, which is a multivariate normal distribution in which the covariance matrix is just given by sigma squared times the identity. Now this identity here means that there is no correlations between the u1 and u2, u2 and u3 and u1 and any, they're all independent from each other. So all we're left with are the variances which appear down the main diagonal. This means that the probability distribution can be factored, in this case, as just the product of normal univariate distributions for u1 multiplied by the univariate distribution for u2 and so on. And the fact that it can be factored is another way of saying that it is an independent, that the u's are independent from each other. From this, we can write down what the likelihood function, because from this expression, we know that u, where I've rewritten it out as a matrix form here, u is equal to y minus this matrix here, which I'm going to call matrix A, which is the design matrix in this case, multiplied by a vector beta of parameters. So now I'm going to substitute this for u, and since this is all deterministic, or is going to be conditioned, sorry, we're going to condition the probability of y on these quantities, we're going to have the probability of y conditioned on A and beta and sigma squared is going to be the same thing as the probability of u, where u we substitute in this quantity. So it's going to be, and this is the likelihood function. It gives us the probability of the data, the y's, conditioned on the parameters. And now we also need a prior for the parameters. We're just going to pick the density to be proportional to 1 over sigma. So that means we're not making any restrictions on what the possible values of beta 1 and beta 2 are. So in principle, we could pick values of beta 2 that would make the system unstable and blow up. So perhaps that's one thing we want to try to infer. We have a short time series and we're running, is this a process that's going to keep growing exponentially? or is it stable? And we can look for that. All right, from this we can get right down the posterior probability, which is obtained as the product of the likelihood and the prior probability. From the determinant of W, we're going to get a term that goes like 1 over sigma to the 2n. We take the square root. This will give us a term that goes like 1 over sigma to the n. When we multiply by the prior, which gives another factor of 1 over sigma, our posterior will have a term that goes like 1 over sigma to the n minus 1. All right, so the posterior probability for the parameters, which are the two coefficients, beta 1 and beta 2, and sigma, conditioned on the data and the model and the background information, is proportional to a term that goes like 1 over sigma to the n minus 1, where the sigma to the n came from the square root of the determinant of W, which was the normalization constant that came from the likelihood function, and another factor of 1 over n came from the prior, which was obtained because we assumed that the prior probability for sigma was constant in the logarithm of sigma. And then we have the exponential term, where the sigma squared comes from the W, right? W is the identity divided by sigma squared. And we're going to rewrite this in a more convenient form by completing the square on this expression. So what we have is, so we have a term which consists of a sum of squares that involves beta, but not y explicitly, and a term that involves y and beta hat, but no beta. So this is just a constant term when we think of this as a function of beta. And so the posterior becomes and I guess I forgot to mention that beta hat, of course, is the solution to the normal equations. All right, so if we care about beta, the coefficient of beta, and not about the value of sigma, we can integrate out sigma to get the posterior probability for beta 1 and beta 2 alone. So the marginal posterior probability for beta alone is going to become and so we're going to use this quantity in a MATLAB script to make inferences about beta hat. All right, at this point, it's good to go to MATLAB. And one thing that you should have noticed is that once I've got to this page, the theory is exactly the same as the one we got for the fitting the straight line. The only difference is that the matrix A now is a different matrix than before, but the math is all the same. So when we do this estimation, what we're going to do is we're going to use the same routine, MATLAB routine we did for the straight line fit. We're just going to modify what the matrix A is essentially. All right, so let's load in the straight line fit from before. At the beginning, I used to generate some synthetic data, and we're going to do the same thing now, except that we're going to generate noise from an AR1 process. There's no need for an X. We can keep sigma for the standard deviation of the noise. We have to assume parameters for beta 1 and beta 2. Then we generate some random noise. And then we give it an initial condition. Let's start it off at just 0. All right, so since y0 is kind of a special case, we have to start off by initializing y1 outside the loop, and then the loop will go from 2 to n. And then we can make a plot of the synthetic data as before. All right, and then we can do our AR1 process. So the columns of A are, remember that what A was, a column of 1s, and this y tilde vector, where y tilde is the vector of y's shifted downwards to start off to make room for y0. All right, so that's the design matrix. Now we can marginalize out to get the probability of beta 1 alone. So remember, when we do the mesh here, the mesh one is like the x-coordinate, which moves horizontally. And so if we want a probability for beta 1 alone, we have to sum through the columns, which is like summing over the first index of P, of the 2D posterior probability. And the spacing is going to be the spacing between each row of the column, which is d beta 2. And similarly, if we want to get the posterior PDF marginal for beta 2 alone, we're going to integrate over beta 1, which means summing along the rows. The spacing between the columns is going to be d beta 1, and we're going to sum along the rows, which is the second index of the probability distribution. And now we can make plots for the marginals. And now here we can write down what the posterior is going to be. And now we have the log of the posterior after integrating out sigma, so the log of this quantity. And then our normalization. And I think that's everything. All right, let's give this a whirl. Hopefully there's no mistakes in it. I'm sure there's going to be. Okay, so I have an X in here, which is vestigial from the last code. That was on line 27. So let's see what I forgot to change over here. So this should have been a column of ones. I didn't define what the R is. So R, that's the vector of residuals, which is Y minus A star beta hat. So this little bit of code here, this is just to help me set the range in which I'm going to make my 2D grid. So because all these calculations get repeated in the calculation of the posterior. So it's a little bit inefficient, but it's a little bit clearer. Otherwise, I'd have to guess at how big to make my meshes and then plot the posterior probability. And if there's quite a bit of probability left on the edges of my domain, then I'd make it bigger and I'd keep increasing it till there was no more probability on the edges of my 2D domain. Almost there. All right, it seems to have worked. So let's see what we got. The posterior PDF for, it's hard to see, huh? It doesn't quite fit. Here we go. Okay, so the posterior PDF for beta 2 is somewhere around here. The maximum, I mean, of the posterior, which is somewhere between 1 and 1.01 or somewhere in this range. I guess we have the value. Beta 2 hat is 1.003. That's the center. And then the true value, what was the true value? Beta 2 was only 0.2, so that's a very terrible fit. But yeah, so what is going on here? Oh, I found the mistake. Here I did y2 to end. That's not right. What I need is y0 then y1 to end minus 1. I was sneaky. So I ended up regressing everything on itself. So that's why that was not good. Okay, now let's clear and start over. Clear all. All right, so now beta 1, the maximum is somewhere around minus 1, which is what we expect because that's how we constructed the time series. And beta 2 is somewhere in the range of, it includes 0.2, which was the true value I generated for the process. All right, let's make the time series bigger and try again. And now we still get the same thing. Now the range is getting narrower and the PDFs are getting tighter. Let's go for even longer time series. Now I notice that the scale, all the significant probability is between minus 1.1, let's say, up to minus 0.8. So it's much narrower in this direction. And similarly in this direction, all the probability is between maybe 0.26 and 0.14, let's say. So they're getting narrower, and we're recovering the correct value. Okay, so the important point is to make sure you construct the design matrix correctly. We're regressing A onto itself, but lagged by 1 time. So if I put y0 as the first entry, then the second one has to be y1, the third y2, and so on. Whereas the y's, they start at y1, then y2.